at Louisiana State University in Baton Rouge, Louisiana. Her research area is geometric group theory, in particular, quasi-isometry invariance of groups. She received her BSc from Mumbai University and earned her MS and PhD degrees in mathematics from the University of Chicago. Before joining LSU, she held postdoctoral positions at the University of Oklahoma Norman and at Emory University, Atlanta. Professor Dani has been the recipient of several prestigious grants and awards, including from the NSF and Simon Foundation. In 2016, she was awarded the Ruth Mishler Award by the Association for Women in Mathematics. Today, as you can see, she'll be speaking on Stallings folds, a topological approach to free groups and beyond. All yours, Pallavi. Please start.
Okay, thanks very much, Sachi, for the introduction, and thanks for inviting me to speak in this conference. It's a real pleasure to do so. Okay, so so I'm going to be talking about a tool introduced by John Stallings back in the 80s as an approach to studying the structure of subgroups of free groups. And so I'm going to start by briefly recalling or introducing you to what this looks like in the case of the free groups, and then later on I will talk about more recent work of my own on a generalization to the setting of right-angled Coxeter groups, and this will be joint work with Ivan Levkovitz from Technion in Israel. Okay, so let me begin with saying a little bit about free groups. So by a free group, I mean a free non-abelian group of some finite rank. And so you can just think of a free group generated by two letters A and B. So this example is a rank 2 free group. So the rank is just the minimal number of generators that you need to generate the group. And if you think about it in terms of presentations, that just means there are two generators and the elements of, and there are no relations. So in other words, the elements of the free group are simply words in the letters A and B and their inverses, and no non-trivial freely reduced word represents the identity element. So these are basically the simplest possible infinite non-abelian free groups that there exist. Okay, so now let's consider subgroups of free groups. So by a subgroup, I mean, it's always going to be specified by a finite list of elements of F. So in this case, W1, W2, Wn are all words in these letters A, B, and their inverses. And so they're elements of F, and they generate some subgroup of F. And it's well known that, in fact, any subgroup of a free group is also itself free. So in that sense, we understand what the subgroups look like. But there's still many questions that you might be interested in about these subgroups. So for example, it's not, even though we know that H is free, it's not necessarily free on this particular generating set, W1 up to Wn. So this might not be an optimal generating set. And so the rank of H could actually be less than N. So the first question that one might ask is, what is the rank of H? And on a related note, what's a basis for H? In other words, what's an actual set of elements that generate H where the number of generators is actually equal to the rank? And then there's lots of other sort of group theoretic questions that you can ask. For example, is H a finite index? Is H normal? Given a word W in the generators of F, is this word actually an element of the subgroup? So I should note that in general, elements of H are products of these words W1 to Wn that we started with. But if you take some arbitrary word in H, it's not necessarily going to be obviously able to be expressed in terms of those generators. So it's a valid question of, how do you recognize when this group is, when this word actually is in the subgroup? This is called the membership problem for the subgroup H. And then If you have another finitely generated subgroup, say K, then you might be interested in, what's the intersection of H and K? So, and of course, there are many other questions, but this is sort of just a list of sort of first questions that you might ask. And so it turns out that all of these questions can be approached using this approach of Stallings folds. But I should say that, all of these are questions in combinatorial group theory, and they all, already had combinatorial solutions to, well, many, if not all of these questions. So this idea of using these folds is more sort of a shift in viewpoint that kind of led to sort of cleaner and more elegant proofs of some things that were already known, and has also sort of fueled further research. So, for example, people, even today, people still study, groups of automorphisms of free groups, and Stallings folds do actually play a role there. Okay, so what are these Stallings folds? So these are some folds are operations that you can do to graphs. So by a graph, I will mean a directed labeled graph. And I'm going to use a sort of a more general definition of a graph, where I'm also allowed to have, so it's a set of vertices and edges between vertices, but edges are allowed to be loops. So you can have one edge having the same vertex as both of its endpoints. And you can also have multiple edges between a pair of vertices. So that's a graph. And then so directed means that every edge has an arrow on it pointing to one or the other of its endpoints. And then it's labeled by some finite set of letters. And you should think of these letters as the generators of some free group, because that's how it's going to be used in the end. Okay, so once you have one of these things, you can define a fold operation. So a fold operation is something which identifies a pair of edges of lambda, which are incident to a common vertex. So as in my picture here, and they have the same label and orientation. So by same orientation, I mean relative to the fixed vertex. So here, both the A's are outgoing. And so now I can identify those, that pair of edges in my whole graph. So, right, so this is sort of just what's happening in the, at that vertex, but, you should think of this as sitting inside some big graph. And so what you've done is produce a new graph with one fewer edge. And then a graph is said to be folded if no further folds are possible. Okay, so let's see how we can use this to say something about free groups. So consider the free group F. Again, let's just, for definiteness, take the free group generated by these specific elements A and B. And let H be some finitely generated subgroup. Again, for definiteness, I'm just going to pick, for this example, a specific example generated by these three elements that I have written down here. So what you can do now is you can draw a graph. You can draw a graph which we call a rows graph. Here my group has three generators, and so I'm going to use a rows graph with three petals. So each petal is a loop, and it's subdivided and then labeled by one of the generators. So this loop here, for example, as I read along it, I read the label with +1 exponent if I travel in the direction of the arrow, and a -1 otherwise. So here this would be A followed by A followed by B inverse, which is the first generator here. And the other two loops are labeled by the other two generators. And so now that I've drawn this graph, I can see immediately that at this central vertex here, I have two edges labeled B that are pointing outwards. And so there's a fold that I can do, and so I do it. Okay, so then that gives me this new graph in which those two edges have been identified. And then I go around and look at the other vertices and see if any further folds are possible. And so in this particular example, I see that yet at the same vertex that I worked with before, there are two A's going out as well as two B's coming in. And so I'm going to just go ahead and fold both of those at the same time to get this picture. And now that I have this picture, I see that, I can sort of go around and check and see that at every vertex, a fold is not possible. So at every vertex, if I look at a pair of edges coming incident to it, then either they have different labels or they have different orientations. And so, so what I have here is a folded graph. And so we arrive at this folded graph, which I will always call lambda of H. So it's sort of the special subgraph that's, it's a special graph that's associated to our subgroup H. And it turns out that this particular graph, yeah.
Sorry, can I interrupt you? How do you, so given the subset S,
yeah,
how many vertices does the graph have? I mean, I know you talked about 3 petals because of the 3 elements in S, but how many vertices? And
it's going to have a lot of vertices because I have to subdivide. So each of these things at the end of a label thing is a vertex. So in this case, right, so you can do a count, but it's going to depend on the lengths of these generators that we have. So here, each of them, there's sort of one central vertex, but then I had to add these 2 extra vertices here, and these 2 here, and these 2 here. So
it's 7. Right.
Yeah, so in this case, it's 7. But in general, it's going to depend on, what I have going on here.
Right,
so,
right. Thanks. Thank you.
Sure. Right. And actually, the number of vertices is going to play a role later on. So we'll see in a minute how that affects things at the end. Okay, so anyway, so this lambda H carries a lot of information about H. And so it can be, for example, used to answer some of the questions that I was talking about earlier. So I'm going to illustrate a couple of them here. But so here's another example that I just worked out. But I mean, so again, so I started with this generating set, which has 4 generators in this case. And then, you can do this sequence of folds, and then you arrive at this situation. And so this is lambda H in this case, this last one. I hope everybody can see when I'm moving my cursor. Can you see when I move my cursor?
Yes, I can see.
Yeah, okay, great. Anyway, so here in the penultimate step, if you see, there's this loop, which is labeled by BAB, sort of hanging down, and a loop BAB going around this graph. And so what's happened in the last step is it's actually a sequence of 3 folds. I sort of compressed it so that it all fits in one line, but 3 folds gets you from this graph to this graph, and suddenly you've kind of killed one of the loops. Okay, and so this is an example of this thing where you started with this generating set, but actually it was not an optimal generating set because it turned out that this last generator was redundant and got sort of absorbed into the rest of the graph. Okay, and so this, illustrates that you can actually detect the rank of H from this final graph lambda H. So it turns out that this H is.
Can I ask something? Yeah. So is the point that as you do these folds, you stay with a set of generators for H always?
Exactly, right. You're sort of, yeah, as you do these folds, you always still stay within this group H. And so you can think of this as...
You get a full set of generators if you look at the petals.
Right.
Okay.
But does the generator reduce or become smaller or something while you fold and all? Is it?
Right. So at each stage, you get a map from... Right. So, I mean, one way to think about it is that at each stage, you can think of these labelings as just a map from the graph into the free group. So into the fundamental group of the graph into the free group. And so at this stage, it's not an isomorphism because you have, so here you have a free group on 4 generators, but you're mapping it into the free group, into F. And then you sort of do the sequence of folds. So the image still generates all of H, but at the end, when you get to this last one, what you get is an actual isomorphism from the fundamental group of this last graph to the actual subgroup H of F. So I don't know, does that sort of answer the question, or?
Is it the same group generated by this? I mean, does it mean that this edge could be generated by smaller number of generators? Is that true?
Yes, exactly. So that's the
Oh.
point. So this is, so now that we have this folded graph at the end, this tells us that 3 is the minimal number of generators that you can use to generate F.
Yeah, Pallavi, but I think the way I understood the question is that you started out with a subset S which had 4 elements, and
Right.
now you found, is it a different subset or will it still be from S itself?
So in this example, it is the same because I sort of, the way I chose my example, I just sort of added an extra generator that wasn't needed. But in general, no, it doesn't have to be from the set.
So it's just an alternate subset which freely generates the whole of S but has the minimal number required to generate H.
Exactly. Exactly.
Okay. Thanks.
Right. Okay. And so, right. And so the point is that, when you get to the end here, you get, so this is a graph, which means its fundamental group is a free group. And and this labeling gives you a map of its fundamental group into the free group, which is an isomorphism onto H. And so that enables you to kind of not only detect the rank, but also pick a basis. So in this case, the way you would usually pick a basis is that you choose a maximal tree in the graph, and then you so then the edges which are not in the maximal tree give you a count of what the rank is. So in this case, we have 3 edges which are not in the maximal tree. So that means the fundamental group of that graph is generated by, it's a rank 3 free group. And then to actually get the generating set or the basis, then you sort of travel along the maximal tree and then do the last edge that's not in there in the first case. In the second case, you sort of travel around the maximal tree to one end of the edge, then do the edge that's not in it, and then go around the maximal tree back to the base point. So that gives you a way of picking a basis for the free group. Okay, so this is a way, right? So this is a way of starting with just an arbitrary set of finite set of generators. You can immediately sort of algorithmically detect what the rank and basis for that subgroup are, or what a basis is. Okay, so another question that I had mentioned was, what's the index of H and F, right? And in order to define the characterization of index, I want to introduce this terminology, which, by the way, is not standard terminology, but it's just convenient because I'm going to use it later. Okay, so I'm going to say that a graph is full valence if every vertex has an incoming and an outgoing edge corresponding to every generator, right? So here the generators are A, B, and then inverses are A inverse, B inverse. So each vertex has to have locally valence 4. It's fine if, as in this case, we've got a loop, so that still counts as 4. But in the first example, you see that there are only 3 edges at each vertex. So this is automatically not full valence. In the second example, if you have to still, so you can see very quickly that each vertex has valence 4, but then you have to kind of go and check at each vertex. So you have to make sure that there's 1 incoming and 1 outgoing A, 1 outgoing B, and 1 incoming B. And so the same thing has to be true at every vertex. And so I've chosen these so that, in fact, both of the second and the third one are actually examples of full valence graphs. And okay, so then it turns out that, H has finite index if and only if lambda H has full valence. Okay, so And then, right, so we said that the first one didn't have full valence, so that means that its index is infinite, whereas these two did have full valence. And so then to compute the index of the subgroup in the free group, you just have to count the number of vertices.
So lambda H in general will depend on your presentation of H, right? Whereas
lambda H actually does not. Yeah, it doesn't matter which generators you originally picked. You end up getting the same lambda H essentially.
okay, thank you.
Yeah, so, right.
So full valence is independent of the set of generators. It only depends on the group, is it?
Yeah, it only depends on the supergroup, the free group F.
Oh, nice.
Right, so free group F had generators A and B, and so now we just have to have that local information at each point. And so, you know.
Sorry, did you say that H is really the fundamental group of lambda H? Did you say that?
Yes.
Okay, so that makes sense. Okay, thank you.
Yeah, so in fact, you know, if you sort of remember back to, you know, covering spaces, you can see that, you know, when you have the situation where lambda H has full valence, then basically what you're describing here is a covering space of this sort of basic example of a rose on two petals labeled A and B. And then you can just use covering space theory, right? So the point is that what you have is a finite finite degree cover of this graph, and the graph with which is the rose on two petals labeled by A and B is has fundamental group F. And so then what you've basically achieved is to realize H as this, realize the fundamental group of this cover as your subgroup H. And so that tells you that it is a free group, that it is, you know, that it has the degree that you think it should, which is namely the number of, the inverse image of the single vertex in your cover. On the other hand, you know, if you don't have this full valence property, then you can sort of construct an infinite set of cosets using that fact. And while I'm on this covering space theme, I should also mention, you know, right, so there's this correspondence between covering spaces and subgroups of the fundamental group for any group, right? Or for any space. And then if you remember, normal subgroups correspond to a particular kind of cover, namely it's sometimes called regular or normal cover, right? And what that is the cover has to have the property that that any vertex can be taken to any other vertex. I mean, in the setting of graphs, what it says is that any vertex can be taken to any other vertex by some label preserving graph isomorphism. So for example, in this case on the very right, you see that if you pick any pair of vertices, there's some symmetry of the graph, which is label and orientation preserving, which takes that one of the vertices to the other. Whereas that's very far from being true in this graph in the middle. So in fact, it turns out that, you know, the graph on the right is a regular cover, whereas the graph in the middle is not. And so the graph on the right actually has a fundamental group that's normal. In F, whereas that doesn't. So I didn't actually make a separate slide for normal, but that again can be very easily sort of seen using covering spaces. Okay, so I've illustrated a few of the questions that you can answer, and in fact, all of the questions that I mentioned in the beginning can be answered using this perspective, and many more. And then, as I said, not only has this been influential in thinking about free groups, it's also been generalized to many other settings. But it becomes a little bit trickier when you have anything other than the free group, because other groups have relations. And the whole point is that this lambda H, this object that you have at the end, is supposed to sort of encode all the information about the group. So in particular, what's true in the free group is that any reduced word which any reduced word in our big group F, which represents an element of H, can be read off as some path in lambda H. And you're never going to be able to do that in another group unless you have some way of taking care of relations. And so nevertheless, there have been a variety of different settings where this has actually been done. So the first people to sort of apply this kind of idea to non-free groups were Arjantseva and Olshansky, who used it to kind of prove that so generic in a certain sense groups have a variety of different properties. And then, there's a sort of list: Coxeter groups, small cancellation groups, automatic groups, and groups acting on cat zero spaces, or certain groups acting on cat zero spaces. Sort of various forms of generalizations of these techniques have been used there. So what I wanted to talk about today is sort of developing a generalization that's well suited to this class of right-angled Coxeter groups. So why this class? It's because I was sort of already interested in this class of groups, and in particular, I needed some of the applications that we were sort of hoping to get out of these techniques to answer some other questions. Okay, so, and before I proceed, I should also say that actually this class of automatic groups, I'm not going to define all these classes, I just wanted to mention sort of other possible generalizations. But automatic groups is actually a very general class, which includes right-angled Coxeter groups. But sometimes when you prove something in super generality, it's not necessarily practical to apply to a specific case that you're interested in. And also sort of specializing to right-angled Coxeter groups rather than this very general class allows you to prove stronger theorems. Okay, so let me quickly say what a right-angled Coxeter group is. Okay, so the easiest way to define a right-angled Coxeter group is it's a group which is defined by a graph. So let gamma be a finite simplicial graph. So what I mean by this is this time I don't allow loops and multiple edges. And so it has vertex set V gamma, edge set E gamma. Then you can define a group based on that graph, which is the right-angled Coxeter group W gamma. And it has as its generating set exactly the set of vertices of gamma. And now you have this presentation where there are two types of relations. Each generator is an element of order 2, and you have a commuting relation between a pair of generators exactly when the corresponding vertices of gamma are joined by an edge. So it's probably worthwhile to do a couple of easy examples just to get familiar with these. So if you have a graph gamma with 2 vertices and no edges between them, then each of these 2 vertices generates a z mod 2z, and then you just get the free product of those because there's no other relations between them, and we sometimes call this d infinity. But on the other hand, if you do have an edge between them, then those 2 z mod 2z's actually commute. So you get z2 cross z2. And then sort of a slightly next level example is that if you have a square, then these opposite pairs of diagonal vertices generate d infinities because there's no edge between them. And on the other hand, they commute with each other. So you get d infinity cross d infinity. So in these sort of basic examples, you can kind of, rewrite it algebraically in some very easy form. But of course, in general, the graph is the easiest way to describe the group. There's, if you try to write down algebraically, it starts looking very complicated. Okay, so that's what these right-angled Coxeter groups are. And this right-angled comes from the fact that, okay, so these right-angled Coxeter groups act on properly and co-compactly on certain simply connected cube complexes with some very nice properties, which we won't really need what those properties are in this talk, but and then the point is that the generators of the right-angled Coxeter group act by reflections in certain hyperplanes. And these hyperplanes intersect at right angles. So that's where this right-angled nomenclature comes from. And so just to let you know, a cube complex is simply a CW complex in which every cell is isometric to a Euclidean unit cube. And then the attaching maps are sort of restrictions of Euclidean isometry. So you could have weird things like cubes being wrapped around, but in the interior of any cube, it's isometric to a Euclidean unit cube. Okay, so that's sort of a picture of one of those. And so these are the objects that we're now going to be working with when we're talking about folding, right? So generalizations of folding. So what we're going to be talking about is, okay, so we start with this gamma. You should think of gamma as something that's eventually going to generate a right-angled Coxeter group. So it has, its vertices are generators of a Coxeter group. And so, but the objects that we're going to be working with in this sort of folding sequence are these, so just cube complexes with certain properties. So the first property is that the cube complexes are what we call gamma labeled. So each edge of X is just labeled by a vertex of gamma, or in other words, a generator of the group. And here it's more convenient to use unoriented edges. This has to do with the fact that the generators have order 2. So it's kind of not really convenient. I mean, so there's no orientation because S is equal to S inverse for every generator. And then we want the property that opposite edges in our cube have the same label. Okay, and so that's because, again, we're working with Coxeter groups, right-angled Coxeter groups. So all of the relations are these commuting relations, which if you write down a commuting relation as a disk with a boundary label with that relation, it looks like a square, right? And so opposite sides of that square would have to have the same label. And then finally, we want this condition that if you have a cube and you look at a vertex of that cube and you look at what the labels of edges incident to that vertex are, then you would want it to be the case that those letters actually label a click in the graph. So in this case, we've got A, B, and C. And the fact that you have this cube here means that in the graph, you would see a triangle. In other words, A, B, and C are mutually commuting elements in the group, and that's why there's this cube which is recording the fact that they mutually commute. Okay, so these are the kinds of complexes we want to work with. And now let's see what modifications we need to do to the original folding process in free groups. So of course we have the analog of the fold, right? So we have, given a pair of edges with the same label, this time we don't have orientations, but we can fold them. And sort of, I didn't make a big deal of this when we were talking about free groups, but there's some other possible pictures that you can have when you're dealing with folds. Okay, so that operation is just like the previous case, but now there's also higher dimensional analog of this thing. So you have cubes, so you might need to identify multiple cubes which have the same boundary. So in this case, this picture is supposed to signify, 3 different squares which are all sort of glued along the same boundary, and then the identification operation just identifies them all into one square. And you can do this in higher dimensions as well. Okay, so that's sort of not too far from where we were, but now this is the part where we need to take care of the relations, so to speak. And so here is something that's truly different, which is that if in your complex you see some vertex with some edges coming out, such that the edges, in this case, red, green, and blue, correspond to generators which are red, green, and blue, and they form a triangle, then there really should be a cube there. And so you attach a cube there. Right, and there should be a cube there because that's sort of going to give you the extra elements of the group, which you're getting from relations within the group. Okay, so you have this cube attachment operation. Okay, and so now once you've got these moves, you need to know, when you're going to stop doing moves. And so we have this concept of folded, right? And so again, it's folded just like it's the same definition as we had before, which is that it's folded if you cannot perform any fold or cube identification operations. But then there's also this idea of cubeful, which is that, so like I said, you could do a cube attachment operation whenever you see a certain configuration in the graph. And so it's cubeful if, you don't really need to do any of those operations. And okay, so let me just leave it at that. These examples kind of illustrate that. So in this example, here A and B commute in this group. And so this graph on the left here has an A going in and a B going in. And since A and B commute, there should be a square there, so it's not cubeful. This is the picture which occurs after I've attached the square. So this really should be shaded in. So this is a square attached here. And now this is cubeful because everywhere where a square needs to be attached, there is a square. Okay. All right. So now we've got this sequence of operations that we can perform. 3 possible operations: folds, cube identifications, and cube attachments. Okay, so given a finite gamma label complex, you can perform these operations. And now we come to another difference between this setting and the free group setting. So in the free group setting, we just started with a finite complex, finite graph, and each time we just folded and we reduced the number of edges. And so we knew that eventually this was going to stop at something where the graph was folded. But here, because we have this added complexity of attaching cubes, there's really no guarantee that this is ever going to stop, right? So that's okay. You can still take the direct limit of this sequence of complexes. Okay, and so, right, so we say that omega x is a completion of x if it's folded and cubeful and arises as a direct limit in this way. And so there's sort of this added uncertainty of whether or not this is going to stop, but at least you know that you can prove that there's always a way of choosing a sequence of these 3 types of operations so that you do actually get one of these folded and cubeful complexes. So there's always, you can always find one example of a completion if you start with a finite x. Okay, so how do you associate it to a subgroup? Well, okay, so now let's go back. This is very similar to what we did in the case of the free group. So if you have your right angle Coxeter group W gamma and a subgroup generated by some finite list of words, then you just do the rows graph just like we did in the other case. Okay, so your starting point in this completion sequence is the same rows graph. Okay, but the difference is that now you might have to, so now you do folds as well as these other operations. And this object that we get at the end is the analog of lambda h that we had before. So I'm probably not going to have time to sort of say and how to characterize any of the properties, but let me at least do a couple of examples to sort of illustrate this definition. So let's say your graph is gamma, which is generated by, sorry, so this is the graph. And you have a group which is generated by these 2 elements, ADB and AEC. So the rows graph that you start with in this case is this graph. Okay. And okay, so you have to just do a completion sequence. So the first thing you see is that there are 2 red edges coming in, and so you can fold those. And then the next thing you see is, oh, here's a red edge, a green edge, and a blue edge. And I see that red, green, and blue form a triangle in my defining graph. And so that means that there should be a cube there. So I attach a cube. And then you can go through and check check all of the vertices that we now have, and we see that there are no other folds or cube attachment operations possible, and so this is the completion. And on the other hand, here's one where it's not going to terminate. So if you have the graph gamma, which is this a square, and group G, which is generated by ABCD, so coincidentally, this also turns out to be a square, then, okay, so what happens is that you start, there's no folds, but you can do a cube attachment, and that means you attach a red-green square, because red and green commute, and similarly, purple and blue commute, so you attach that square. And then it turns out, oh, green and blue commute, so you attach a square here, and red and purple commute, so you attach a square here. And you can see that this process is never going to end. It's a periodic thing. And so at the end, in fact, you end up with this infinite, bi-infinite cylinder, which is tiled by squares. So that's sort of the other extreme. And okay, so anyway, so since I'm essentially supposed to stop at this point, let me just say, so these objects kind of characterize some of these other properties. And so let me just verbally say what it is for the finite index case, right? So it turns out that for finite index, what you need is that the one skeleton is full valence like we had before, but also it has to be finite. So in this case, here we have the one skeleton is full valence, but it's not a finite complex. So this is not a finite index subgroup. But on the other hand, in our previous example here, this is finite, but it's not full valence. So this is also not a finite index subgroup. So you have to have both those properties to have a finite index. And yeah, so let me stop here.
Thank you. Thank you, Pallavi, for a wonderful talk. Some applause for her. Are there any questions?
Yeah, Pallavi, this last graph,
My example?
commuting one, some that not fold at the end, you got this infinite cube thing.
Yeah.
What does it mean? Does it mean G is a billion? I don't understand that exactly. So
G is actually just a cyclic subgroup. So it is definitely an abelian group by itself. Yeah, you're right. So this, in fact, the fundamental group of this object is G. Because, okay, so in general, you can't talk about fundamental groups because these groups have torsion. But if you take a torsion-free subgroup, which G is, then it turns out that the completion, the fundamental group of the completion is your subgroup, just like in the free groups case. And so, yeah, so this is a cylinder. So its fundamental group is Z. And you can see that G is generated by one infinite order element. So it is also Z or Z. Yeah.
Thank you. Very beautiful and wonderful talk, Pallavi. Thank you.
Thanks.
Are there any more questions? Any comments? In that case, let's thank the speaker again for a really beautiful, lucid talk. Thank you, Pallavi.
Thanks.
I think she can't hear our applause, but we can imagine everybody clapping for you. Thank you.
Sachi, you might want to put your video on if possible, because thanks.
It's going off for some reason. I think I did.
Okay, yeah, I think people in the chat are saying that whoever speaks should put their video on so that speaker can see them.
Absolutely. Yes. I hope everyone.
Well, thanks for the invitation. Sorry, I'm going to have to miss most of the conference since it's the middle of the night for me. But
much, Pallavi.
We are glad you could make it. So, yeah.
Okay.
Okay. So,
Bye.
Bye, everyone.
Bye. Okay, so do we have time for a break or should we start straight away?
I think there is no time because it's 1 minute. So
1 minute. Sauli is here. Hi, Sauli.
Hi.
Hi.
Can I share my iPad? I will be using my iPad and writing.
Share.